Hello, now started to introduce variance, and previously all our focus is consider the asymptotic case, and when we consider the variance, it is much more complex for the asymmetric distribution. And Daniel indeed is the first who considered this issue in his Lemma paper, and also the same as he considered the linear combinations of order statistics. He states that comparing the efficiencies of various kinds of estimators is useless unless they tend to coincide asymptotically. So this is, for example, you can imagine that if for a symmetric distribution, this is the sampling distribution of the mean, and the underlying is the median. And then if we just estimate the standard deviation of these two sampling distribution, we can estimate the efficiency, comparing the efficiency, right? But if they are different, and then there will be a very serious issue, because for a very large estimator, the variance, it will tend to be larger, right? And for a very small estimator, the variance, of course, it will tend to be smaller, right? Maybe 1 or even 1, right? So then there is an issue that if you compare the variance of a very large estimator, if the value is very large, and then if you're comparing it to a relatively value is very small, then in most cases, especially if the deviation is very great, and then no matter in which cases, you will get the result that the values will be much smaller for a value with a very small, much smaller estimators. But this is maybe maybe it is the case, for example, for a school distribution highly with a very high criticis, and the median normally should have a higher efficiency than the mean, because But we sometimes question that. First, even the median is better than the mean, but how much it is better? It should just be a little bit better, right? In most of the cases, and that means how we can estimate minimizing the impact of due to the change in the scale. And so Bickel-Lehmann they suggested a method that using standardized variance. And basically, they first computing the variance of the standard sampling distribution, and then divide it by the parameters square. We estimate it. So this standardized variance is a post correction to standardizing it, and then comparing it. This is of course a very nice approach. A drawback of this approach is that there is an inverse square dependence on the standardized variance on theta. So therefore, it's the scale standard error I propose here. It was inspired by their approach, but the difference is that I do a pre-correction before. The correction is before estimating the standard deviation. It is times, for example, here's the mean 1, 3, 6, okay, and then trim mean, yes, 5, 4, 5, 10, 7, Windsor rise mean 5, 7, okay, and then first the scaling. First, you need to using a scaling factor, that is computing the mean of this first, for example 10. And then computing the mean of the second column, which is 16, and then the mean of another column, 22, and then you divide it all this with the mean. The first is 10 divided by 10, it is equal to 1. 16 divided by 10, it is 1.6. 22 divided by 10, it is equal to 2.2. And then multiply this scaling factor, this matrix, with the original matrix, and then it will form another matrix. This new matrix is like this, multiplying this, yes, and then dividing 1.6, dividing 1.6, okay, dividing 2.2, dividing 2.2, dividing 2.2, okay, and then in this way, this is the result, and then we estimating the unbiased standard deviation of the corresponding columns. These columns, it will be the result. So this way has the advantage that. First, you can see that because it is just dividing a scaling factor, so the impact on the scale of this is much smaller, because it is just a ratio. So, for example, if it is 110, and then you just multiply by 10, so it does not multiply by 100. So it is not highly depending on this. It is not much better than this inverse square situation, that it will greatly impact this variance. So it is a very small correction, and using this correction, normally after corrected, it can achieve a result that can make the other estimators that is very comparable to the sample mean. And this is also very important. I can show you, for example. Yes. For example, here you can see this scale standard error. They are pretty similar. Right? You can even for very different estimators, they are pretty similar. And this is because depending on the sample size, it is the sample size is right for 5,000 around 5,000. So the square root of 5,000. You need to consider that, so it is a little bit very close, and then to the standard deviation. This in this way that it will produce a result that very close, because the sampling distribution of the sample mean was guaranteed by the central limit theorem. So we want to produce a scale standard error that is very close to this to the standard error of the sample mean, and indeed our guess is correct that for most estimators, for example, this is not shown here, for medium trim mean, for many robust estimators, although their variance are a little bit different, but this difference is indeed relatively small, and they are generally very close to the sample mean if without using the scale standard error. And even if we consider the central moment, it is similar. That if you consider the mean, because they are essentially the mean of the central moment kernel distributions, and although they are not exactly, because the kernel distribution is not independently identically distributed, but generally it's very close. And but a drawback of the scale standard error is that you need to be aware of the case that the scaling factor cannot be 0. If it is 0. And if yes, it cannot be 0. This if it is 0, of course you times something 0, and then these things will be totally changed. And especially this mean, this dominant cannot be close, so it cannot be used for the symmetric distributions of the location or odd ordinal central moments, and since they will be 0. And also, after I proposed this scale standard error, I do some simulation experiments, and then I found a very interesting result that for most estimators, the scale standard error basically between the medium and central moments. It is a little bit like that. Maybe sometimes the medium may decreasing. Yes. For example, here is the keratosis. As the keratosis increasing, the scale standard error of this medium decreasing, or maybe sometimes it may be also increasing. But generally, and then for the sample mean, it always increase as the keratosis increase. And then the most interesting thing is that if you consider other estimators, and then their variance are they are within these two bounds. Within this medium mean bound, or the medium central moments and U central moments, essentially the mean central moments within these two bounds, and for most estimators. And because there is a similar monotonic relations between the breakdown point and the variance, also very common, just like Bayer's, for example, Bickel-Lehmann, they prove also in their lemma paper descriptive statistics for non-parametric models, and they prove that there is a lower bound for the efficiency of the trim mean to the sample mean, and this bound is a monotonic, obviously, right? So, however, the direction of monotonicity can be different. For example, if you use the Lehmann-Scheffel theorem, it can prove that sample mean and the second moments are the unbiased minimum variance estimators. And for the Gaussian distribution, so when the keratosis is around 3, sample mean is generally the optimum. But when the keratosis is higher, when the sample mean, of course, it becomes much less efficient, and it totally breaks down. So when the second central moment becomes infinity. So but for the medium, the case is very different. First, it is of course much less desired, but then even it is infinitely large. This medium, it is still valid for distribution with infinite mean. It is still valid. So that means that if we consider there are many other estimators. So that means the optimum choice, if we just consider robust estimators, because sample mean is not robust. So there is a problem that, for example, for other robust estimators, it might be better than the sample mean, but it is much less desired. It might be less desired than the sample mean, but better than the medium in some cases. And then you can see that then there is an issue that if the variance optimum choice can be different for different keratosis. For example, here, if you just consider this 3, and then this is not robust, so the optimum choice will become this estimator. And then if the keratosis is here, then the optimum choice will become medium, right? So it is a little bit. It reveals it suggested that indeed we can do something to select the optimum choice of the optimum choice. And this approach was probably first proposed by Lai, Robbins, and Yu. Their PNAS paper proposed an estimator that adaptively chooses the mean or medium in a symmetric distribution, and they use the bootstrap estimating the standard errors, and they show that the choice is typically as good as the better of the sample mean or the medium regarding variance. And so they for example here, and basically they can construct an estimator whose variance is like this, yes, like this. That is always close to the optimum choice, because that is always close to the optimum choice. Yes, very close to like this way. So it is yes, it always close to the. So this is very desired, and another approach was deduced by Laplace, and they deduce using a parametric assumption. They deduce the optimum weight because they use it combined. They suggested that this is the sample mean and also medium. And they suggested a weight that they suggest this estimator, and so for each different classes they can deduce a different weight. So this approach is a little bit more accurate, but it requires stricter assumptions. And our approach is indeed first inspired by Lie, and I use many. You can because for many this symmetric weighted Hodges-Lehmann central moment, there are many possible estimators. We can use the trim mean, Winsorized mean, Hodges-Lehmann estimator, trim Hodges-Lehmann mean, medium Hodges-Lehmann mean, Winsorized Hodges-Lehmann mean, binomial mean, stratified mean. We previously defined many mean estimator, right? So those mean estimators we can we can use, and then because for the Coriolis you not only need to consider the fourth central moment, you also need to consider the second central moment, the variance. So therefore, in total, there can be here, if the breakdown point is 1/24, there can be 364 different combinations, and then among so many combinations, so we can find, but here we use the root mean square error. It's not the variance, because the scale standard error is just considering the variance, and root mean square error is considered the overall not only bias, not only variance but also bias. And then we can find that, for example, and then for each combination there will be a root mean square error for different classes, right? And then this although it is very difficult to analytically solvable, but we can easily determine that using a Monte Carlo study. So in this way, we can just if we know the classes, after we determine this function, we can directly determine the combinations with the minimum root mean square errors, right? So in this way, we can similarly using the iterative reweighting algorithm that, for example, we previously used. You can determine the classes using a shift scale distribution or even multiple consistent distribution. And after determining the classes, you can just find the minimum, the best combinations with the best variance. Yes, and then you can even further iteratively reweighting that. For example, you find the best estimator with the best variance. You can use this, and then this classes further estimated it to find a better guess, and it is possible. And here, this is this approach, and another slightly approach is more complex than I introduced here. But generally, the variance of in this way, the selected combination, I call it invariant central moments, or invariant standardized moments, and in general, the invariant central moments are the variances are much more efficient than unbiased sample central moments. Generally, yeah. So this is a very surprising result, because you need a reminding that the is better, yes, generally, and even as for example, you can see here. Yes, it is the efficiency. You can see here the efficiency generally is better, and it is not surprise, because for the invariant, because the invariant central moments are based on U statistics, and sample central moments are, I mean, their computation is relatively much less computationally efficient. So their efficiency is higher than the sample central moment, and if you consider the overall errors, and they can be similar, and that means but more importantly, the invariant central moments are robust. And so therefore, in this way, we can construct an estimator that is with a very small bias, and even zero bias for many different very different distributions, and even for some slightly distributional assumptions slightly wrong, this is still valid. And also this estimator is very efficient, and more importantly, it is robust. And so this is the advantage of our invariant moments.